All right, again, thanks for coming. Today we're going to talk about the mountain belt and some new observation in mountain belts. Okay, so I'm not going to talk much more. Please come in. So I'm going to let Danny now introduce the speaker today. Okay.
Good. Do I need to hold this?
Yeah, you need to hold it.
Okay, good. All right, well, thanks very much for coming today. It's my pleasure to introduce Dr. Liz Catlos Jutlashova to today's seminar, our very own. I'm really, it looks maybe somewhat formal. I'm not introducing her as a chair, but we've been friends for a long time. And as I said, you know, there's nothing I could say about Liz that would not incriminate myself as well. You know, she was office mates with my wife at UCLA, so we've known each other for a very long time. And so Liz got she got her BS in chemistry with emphasis in earth sciences from the University of San Diego. She got her PhD from University of California at Los Angeles. She's afterwards a postdoc at the Smithsonian and has been as a faculty member in the Department of Earth and Planetary Sciences now since 2009. She was the recipient of the very prestigious Donath Medal from the Geological Society of America. She's received Nebel Awards. She was a Max Kade Distinguished Visiting Professor at the University of Heidelberg a few years ago. And so, you know, there's a lot more I could say about her. She's been very involved with the E-beam lab here. She's been, you know, an instructor for Geoforce for many years. But in terms of her research, she has been really, you know, at the forefront of petrochemistry and metamorphic petrology, you know, sort of probably an early petrochronologist, looking at monazite and garnets to understand tectonic processes. She's worked in the Himalayas, she's worked in Turkey, she's worked in Slovakia in recent years. And so she, you know, so it's exciting to hear about her new research. And she definitely wins my, like, you know, sensationalist title. So we're all here for Aftershocks. So with no further ado, let's Catlos.
So thanks so much for coming. Before I get started, I definitely want to acknowledge my co-authors here in this paper, both in the US and India. Stole the title from the Netflix documentary, Aftershock. Have people seen it, Aftershock? We haven't had a single person in the audience who hasn't seen this Netflix documentary. It's fantastic. Afu's seen it, yeah. Luke made it plural. The Netflix documentary talks about the aftershocks associated with the Nepal earthquake, really from three different perspectives, from Everest, from Langtang Valley, and from people affected in Kathmandu. If you've seen it, I'm going to walk you through those field areas and talk a lot about the geology of that. So this weekend, you got nothing better to do. You want to learn more about earthquakes. I think in the geology department, sometimes we get removed from these pretty horrific events. This was a magnitude 7.8, happened in April 2015, came with a friend. 17 days later, magnitude 7.3. Okay, not very large of a magnitude. This is a problem in terms of the geophysics community had told us that the next big one to hit the Himalayas, Nepal in particular, was going to be a magnitude 8. This is much smaller than expected. Maybe like 7.8 is not, yeah, in the terms of our understanding of earthquake magnitudes, this is in the realm of destructive, but not catastrophic, okay? It wasn't at the depth that was predicted. It wasn't, okay, not predicted, forecasted, as Luke says in his email. It wasn't along the fault systems that were forecasted. It wasn't in the location that was forecasted. There's a big time problem here. It was in fact found along a structure, or very close to a structure, that geologists for many years, despite my work and the work of other people, had told us that that fault had died 20 million years ago. And the question is, like, really why? What's going on? And there's not a small number of people who are feeling sort of the impact of this situation, like, why is this? And so, as Danny says, I'm a metamorphic petrologist. I've been interested in the pressure, temperature, time constraints of the Himalayas for a long time now. And so why am I talking about earthquakes? Well, to understand how my rocks get to the surface, I need to know where the faults are. And in terms of the faults, we work with structural geologists. I'd like to think about the architecture of the Himalayas. We have a very nice framework for how we think the Himalayas were created. The structural geology community and the geophysics community obviously work together to try to understand the dynamics of the range, and they inform each other. So me, in this little realm here, I have my eyeball on what's going on in terms of the geophysics community and what's happening in the Himalayas. There's also another sphere here called geomorphology. So I think in recent years, the tips and tools and techniques that we use to get the metamorphic history out of rocks has sort of exponentially increased, and we're able to track higher and higher resolution records from metamorphic assemblages. And I'm going to argue near the end of the talk that we can use metamorphic rocks to say something about erosional processes. The Gorkha earthquake was a devastating event, but not just for ground shaking, it was the landslides. Okay? And the landslides were in fact incredible and killed quite a few people. So overall about 9,000 people perished in this single event. It was, the aftershocks were not just geological, they were also political. It was really a pretty incredible event. I've always been interested in it. The GSA paper, I chaired a session with Anke Friedrich, who's a well-known geophysicist at the University of Munich, and a bunch of other people, including some of them who experienced the earthquake firsthand at the GSA meeting that happened after the event, and we have a GSA Today paper. I'm part of a 3-part AGU Books project. This is the first book that just came out recently with my collaborator, Ibrahim Shayman, and I have a review paper on the Himalayas in this book talking about compressional tectonics. And when I was writing that review paper, I'm like, what's new? There's I think COVID actually had some impact. There's not a few number of review papers on Himalayan tectonics that came out during the COVID time frame. Okay, there's about, from everything that you'd want to know about the Himalayas, people were writing about. So when I was writing that paper, I'm like, what's new? And in my mind, not much has changed since I was working on this with Danny and Lisa back in the sort of late 90s. Okay, so I'm going to talk a lot about the rocks. We are going to see the beautiful mountain range, but we have to have some sort of context. So this is the Himalayas. So how did this sort of complex architecture come to be? Well, India, as an island, marches away from Gondwana, moves about 60 degrees latitude in short order, and hits up, probably first up here in Pakistan around, 60, 70, 50, 40 million years ago. There's a lot of people who are interested in that timing exact, and a lot of different ideas about how the collision proceeded. Were there anything in front of the Indian island that kind of got caught up in the collision? Well, India hits Asia along this feature here called the Indus-Singh post-suture. It's a very complicated suture zone. It has compressional, extensional, strike-slip tectonics, Asian rocks to the north, and basically the Indian craton, the Indian island, breaks up along large-scale, laterally continuous units. And so you can see these units, named out here, basically extend the entire length of the Himalayas. We're going from Pakistan, India, Nepal, a little bit of India again, out to Bhutan. These are large, laterally continuous units separated by laterally continuous structures. There's just a few of them. So we can go through them, and blue is going to be the Indus-Singh post-suture, and blue is going to be the Tethian Formation. These are limestones. These are sedimentary rocks that are up at the top of Everest. They're separated from metamorphosed clastic sediments in pink here that we call the Greater Himalaya crystallines. These were sediments on the leading edge of the Indian island that went beneath Tibet, came back up to the surface along a large fault that we call the main central thrust. Okay, the main central thrust separates the Greater Himalaya unit from what's known as the Lesser Himalaya Formation. These are rocks that can be correlated to what's on the Indian island today. tell you right now, the Gorka earthquake occurred very close to that main central thrust. You have the main boundary thrust separating out the greater Himalaya crystallines from the lesser Himalaya formation, and then in dark brown here are clastic sediments that are shed off of the ever-growing Himalayan mountains getting deposited into a foreland basin, and those are getting incorporated into the range itself. If you looked at this in terms of timing, you have the suture hits first, then around 20 million years ago, the main central thrust is operating, maybe coevally with a large-scale detachment that we call the South Tibet detachment. I'll show you a picture of that in a little bit. The idea with the South Tibet detachment is that the mountains rose so high that they're falling back down. So we have a large extensional structure there that's kind of extruding the greater Himalaya unit. Around 10 million years ago, the main boundary thrust is active, and the presently active fault, the one we thought for sure we'd see something with the Gorka earthquake, is going to be this main frontal thrust here. This map was constructed, before I get to that, there are parallel chains of granite bodies. At the top of Everest, very close to the top of Everest, I'll show you a picture of them, there's granites. Might be surprising to some of the students. You're like, how do you get granites at the top of Everest? You know, that's kind of crazy. Couple of different ideas that they were generated at depth, and the melt sort of migrated through the greater Himalaya crystallines unit. The other is that the South Tibetan detachment, this extensional fault, moves so fast that it caused decompression melting, so you get melts up in there. It's another North Himalayan granite, sort of different chemistry, different ages. This map was constructed by Onion. Several of us knew him also at UCLA. Kind of sad he passed away this summer doing field work. I had the chance to go to the Himalayas with this amazing structural geologist. Here he is. He's sending us a message. He's in the main central thrust shear zone right there and is indicating some incredibly contorted and folded rocks. This was our field team. There's me in the center. There's Mark Harrison, also from UCLA, who was really integral in the early part of my research in the Himalayas. Dick Marston, who's at Kansas State University, who's a geomorphologist. It's really wonderful to go to the mountains with people who have a completely different sort of perspective and who like to see the shapes of the topography, can tell you something about active tectonics. And then I have two colleagues, Dubey and Dr. Pandey, who are both at University of Delhi. Here on is also within the main central thrust shear zone. Drive through the range, drive across these major structures, collect the metamorphic rocks, and try to back out their pressure temperature histories. So where we're going to go next is I'm going to take you to where Aftershocks was filmed. It's really sort of three major areas. We'll go to Everest. I'll show you the rocks there that I just talked about. We'll go to the central area of Kathmandu and talk a little bit about the geology there. And then up in Langtang Valley, which is really important for us as sort of petrologists. So in this talk, we're going to really be moving across the range, but we'll start there first. So this is Everest. This is Everest Base Camp. When the earthquake happened, there were several people who passed away within the base camp itself, not necessarily due to the land shaking, but they were massive landslides that came from ice and rock and debris falling from these incredibly high mountains. The rocks that you're looking at here are the greater Himalaya crystallines, and you see this mountain peak at the top. It's a little bit over 22,000 feet. That's the granite. It's like pretty spectacular to see molten rock at the very top of Everest. When the earthquake had occurred, it occurred in the afternoon. Several of the climbers had left base camp and were on their way up to Everest. Okay, this is Everest in 2019, right? This is a whole set of people who have paid anywhere from, 16,000 to over, 200, 300,000 for their chance to climb to the top. And when that earthquake happened, and what they are, this is the Tethian Formation. This is basically limestones. They're crossing over that South Tibet detachment to get to the very top. There were 140 of these people had to get rescued from the top of Everest after that event. And some of them didn't want to be rescued. They were like, look, we're up there, paid all this money, Let's keep going. And some of the resources that were used that could have potentially been, applied to people who were really in danger were applied to sort of save some of these characters. And if you keep track of Himalayan climbers, you'll know what I mean by characters. Okay, so this is going to be the Tethian Formation. These are limestones, and I'll tell you what's absolutely interesting is that these are the same rocks that if you correlate them, that's what's under Kathmandu. So what's in Kathmandu Basin, or is that particular rock formation. So this is what was happening. This is the helicopter rescue. Because we're geologists, rocks in the foreground are going to be the high Himalayan granites. Okay, and then here's a quote from one of the climbers. Listen, we don't need rescuing from base camp. Many of us still want to climb. And they were experiencing aftershock after aftershock, and I'll tell you, it was a real incredible rescue mission. They were rescued from Camp 1 and from Camp 2. The helicopters made several trips to get all of them off the mountain. This is the other part of you can watch the documentary. It really gets into the rescue mission. It's quite fantastic. This is the Langtang Valley. This is very much known to us as metamorphic petrologists. This is where the main central thrust outcrops, and it shows a very interesting type of metamorphism called inverted metamorphism. And this is where you go from structurally shallower levels, the rocks get hotter. It's a complete opposite way of thinking about metamorphism. Usually you go deep into the earth, the rocks get hotter. Here it's different. It's the exact opposite. So it's a place where it's like on the bucket list of Himalayan geologists to go there, at least those studying the metamorphic rocks, to see it. So what you're looking at here is the Lesser Himalaya Formation, and what's coming in through this area is the main central thrust. So the documentary will show you what happened basically during the Gorkha earthquake. The entire the entire town was basically devastated by a massive landslide, covered it, and this was only one of several thousands that occurred during this single event. This is one earthquake covering this entire valley, and the documentary talks about two climbers who had actually left Langtang Valley in the morning and returned to find it this way and sort of their experiences. There's a really great science paper that came out. You can see that the mass movement happened up here, probably in the greater Himalaya crystallines. The landslide went airborne and buried Langtang village. In red is going to be the damage to the rocks that occurred just during the air blast of that landslide. And then in purple, the rocks actually came up the cliff and came down like a wave. So it's a very, very spectacular event. Okay? And it was just during one single event. So I want you to keep that in mind as I try to go through this talk. Here's going to be Kathmandu. Okay, it shows extreme relief. This is on a clear day. It's a photograph that I took off of, I think it was on Facebook. I just really like it because it shows sort of the basement sort of how low it is and the extreme relief that you can actually see Everest from Kathmandu on a clear day. Kathmandu is basically in a basin, and those rocks that are at the top of Everest also comprise some of the sediments under Kathmandu. Not the best place for you to see the relief, though. I think just east of Kathmandu is this town called Pokhara, and you can see the extreme relief. So if any of you are marathon runners, going from Pokhara up to these high peaks is basically 26 kilometers. The rocks that you're looking at the top are the greater Himalaya crystallines. Some of these are going to be the Lesser Himalaya Formation. Then in the foreground, these are actually erosional sediments. That's the swallows. And you can see where the geology is coming into play. You have large-scale, laterally continuous rock units separated by laterally continuous structures. It's really like a sort of a beautiful architectural arrangement here, and it continues all the way across the range. Here's just, for example, Kathmandu, couple of examples, just so you can see that it's basically going to be in a bowl. It's a bowl bounded by two sort of normal faults, and we're beginning to see sort of the architecture of the Himalayas in this one image, that you can see a lot of the faults of the Himalayas eventually sold at a common dicom on a depth that they call the main Himalayan thrust. And we think that the Gorkha earthquake, there are some interpretations that the Gorkha earthquake occurred kind of at that conjunction of the main Himalayan thrust and some other fault systems. So effectively, this picture is also showing you this Apple paper is fantastic for having before and after images. There's a huge number of historical sites just in Kathmandu that were basically damaged, and the ones that they're still sort of recovering from it all. But it's basically not the place to be in Kathmandu, which is going to be a sedimentary basin that really experiences the ground shaking. This is just some of the pictures of what happened in Kathmandu. But keep in mind, just outside of Kathmandu, you had these incredible landslides and rock falls. And if you go to sort of the disaster management handbook that came out recently, most of the damage is not necessarily in the city of Kathmandu that you would expect as geologists. It's a sedimentary basin, it's in a bowl. But a lot of the death and destruction came out of these remote villages where you had rock falls and landslides. And it plays a major role in sort of the how they evaluate what was severely hit versus crisis hit. Okay, so getting back to the geophysics of it, here's going to be the sort of one of these interferometry images. You have the earthquake occurring here, Kathmandu is going to be here, and you have the aftershock that happened about 17 days later. Now this was very confusing because the way that the sort of the motion operated is that it moved towards east of the epicenter. And so you can see this main Himalayan frontal thrust here that was really largely predicted to be the next major structure to experience seismicity, and instead the aftershock kind of occurred in the exact wrong location, almost just to the east instead of to the south. And so this was very confusing in terms of how we understand Himalayan architecture. And so this is it. This is what we would call probably like the Holy Grail of Himalayan cross-sections. It's what we operate on. You can see here you have these major Himalayan faults. Here's the main central thrust. There's the main boundary thrust, the main frontal thrust, all soling at a common decollement depth that we call the main Himalayan thrust. And the idea in terms of Himalayan tectonics is that basically the active structures are going to be the main Himalayan thrust and maybe these guys out here in the foreland. Notice the Indo-Gangetic Plain, which is going to be the Indian indenter, is modeled as a rigid indenter. It's basically an island that's coming and smashing into everything. In the in-sequence deformation model, you're going to have the main central thrust be active 20 million years ago, the main boundary thrust be active 10 million years ago, the main frontal thrust is active today. I don't believe that at all. I think these faults are moving today. Okay? And I'm going to try to convince you of that by the time we end here. That cross-section has its roots back in the late 90s. This is basically when it was first constructed. How have we moved from the 2000s? Well, we added a few more horsts, okay? And then where did this guy come from? It came from the early 80s, where you basically modeled Himalaya as a large accretionary wedge, like in a subduction zone. But what we did in the 90s is that we added rock layers, and now in 2000 we added more rock layers. Okay, that's what we're doing. We're creating a fold thrust belt. I think we should go back to this way of thinking, okay? And I'll try to talk to you about why we should. This came out in a recent Billum paper about how Himalayan earthquakes operate. If you've got low magnitude earthquakes, you'll be here. So you'll notice this is the same sort of Holy Grail cross-section where you have the main Himalayan thrust coming down and all these faults kind of coming through. If you're less than magnitude 7, okay, you might be operating in this strain accumulation zone. If you're between a 7.5 and an 8, well, it's because the main Himalayan thrust moved and you might get some activation of some faults closer to the foreland. But a big creature, that's going to move the entire décollement. And so this is what we were anticipating. Instead, we got something like this, right? So these were the predictions. So you can see here's the 2015 event, much, much smaller than anticipated. You had all of these sort of pins here. They predicted that you would get an 8.2 in that Pokhara area that I just showed you. You get an 8.7, an 8.4, an 8.5, and what's going to go is that main Himalayan thrust. That didn't happen. And the question is, why didn't that happen? And if that's your cross-section and that's your architecture, is this correct? Or are there other structures that we should be considering to try to understand why we had this sort of moderate event? Okay, and so this is kind of, there's no doubt this is what people are out there in the literature. This paper just came out in 2022. You had the Gorka and its aftershock, put them on the main Himalayan thrust, and let's go home. We got our architecture, everything is good. The problem is, if you look at it in detail, have like kind of my interpretation of it, initially the epicenter was on the main Himalayan thrust, but as you start to do these calculations, that hypocenter moves to shallower structural levels. And you're just like, what's going on? It's not on the main Himalayan thrust, what's happening here? And there are smarter people than me who will take all of these earthquake epicenters, so there's Kathmandu, and you can see all of these black dots are the earthquake epicenters, project them on C to C prime, and you see they form like this really kind of crazy scatter. These are all the hypocenters affected, and these are all the aftershocks after the main event, the Gorka event, projected on a cross-section, and these are all of these different geologists and geophysicists' interpretations of what the main Himalayan thrust looks like. It's like, where is it? Shouldn't we be able to see this thing? And so the geophysicists started looking around and trying to understand, are there other faults that are out there that we should be considering? And they popped up with these different lineaments. These lineaments are showing up in the literature. And what the heck are these things? The Judy lineament, the Thapel lineament, the Goy-Shankar lineament, the Everest lineament. Why don't you just call it a fault? It's not a fault. If it was a fault, you'd call it a fault. It's not. It's a lineament. Okay? What's a lineament? It's some sort of linear feature in the crust that we don't know what it is. It's like seems to appear there. And these are all sort of parallel creatures. And the geophysicists are like, what are these things? Do we need to consider them in understanding sort of how this thing came through? So where are they getting their names? Well, back in the late 80s, in the heyday, the Indian geologists went through and mapped these creatures. And we're looking at it going like, what the heck are these things, right? And they appear to have some element of strike-slip motion to them. Could some of these be strike-slip faults, right? And so where we're looking at here is that you basically be, Kathmandu would be somewhere in this sort of mess. And these things are coming up in the literature. So here's going to be that Judy and the Goy-Shankar lineament. And the 2015 event, we're basically bracketed between these two lineaments. Yeah, we know nothing about these things. We don't know if they're faults. We don't know how deep they go. They kind of cut the major Himalayan structures. And this paper and others will argue that that rupture dynamic was controlled by those lineaments. Well, how the heck does that control a rupture dynamic? I don't know. Something we should think about. Some people have been adding senses of motion onto these things. So instead of thinking them as strike-slip structures, they're actually compressional structures. Well, how the heck does that work with our overall architectural framework? And you can see that they're deciding, maybe not to plot up some of these things, because where are they exactly? And so here's some other ones that are kind of coming through. It's a bit sort of chaotic, but it's definitely coming into our understanding. We're recognizing that to explain the dynamics of that event and the aftershock, that it's not working out too well with our standard framework. This is another example. This is one from Mary Hubbard, and she's plotted up some of these things, but she's also thinking about what's going on with that rigid indenter. Does it have lineaments? Yeah, it's got lineaments. The Indian craton itself is chock full of these things. These are old ancient faults and massifs that are effectively getting fed into the Himalayan range. And so we, can have talks in this department about subduction zones and what happens when a seamount enters a subduction zone. Well, nothing good. Well, what happens when these things enter the Himalayan collision? Well, don't worry about them. They're not part of our overall framework. Let's not necessarily consider them. Okay, and this is a map. The Indians have been mapping the lineaments not just on India, but also in the Himalayas. These are hugely important for the Indian government to know where these are, because not only are they potential seismic hazards, well, these are also controlling the courses of some of their rivers. This is where their major aquifers are kind of getting set up along these things. This is where their ore deposits are found adjacent to these lineaments. It's really important to know where they are. Okay, and they are also seismically active. So these are some, you know, maybe they're not going all the time, but some of these lineaments have sustained some significant events, including most recently the Bouge earthquake, which you could argue with me that's on a plate boundary. Well, it's considered a stable, an earthquake that occurred within a stable continental region. If you just look at South India, these are some of the lineaments, okay? It's chaotic. The Indian indenture, no doubt, is an indenture. It's probably solid. Doesn't necessarily mean because you have a lineament, it's a weak zone. But that's getting fed into the Himalayas. What's it doing? And so if we're wondering what is getting fed into the Himalayas, well, the transgangetic plain, the upper gangetic plain, the middle gangetic plain, and the lower gangetic plain. Sounds good. It's a plain. It's getting fed into the Himalayas. Well, under the plain, you have basins, massifs, ridges, depressions. You have, in fact, a plateau, and this plateau, you know, when it's subducted, it also created a very large magnitude earthquake. What the heck are those things doing as they get fed into this entire system? So, in conjunction with my collaborators on the first slide, we actually compiled where are these lineaments in sort of modern times. So we started with that Dasgupta framework, we took the Indian framework, and there are people, boots on the ground geologists, who are coming through and actually mapping these things. And so we decided to map the Himalayas, identify them. We've identified a minimum of 62 of these different lineaments, and we've classified them into different categories. You have origin parallel strike slip faults. This is the latest, greatest in Himalayan geology. There are major strike slip faults that are coming through this mountain range. People are trying to understand, you know, what's their offset, when were they active. You have these crazy lineaments in some cases sort of cross each other, and you have tear faults that are coming through and sort of joining the major Himalayan structures. And you may look at these and just be like, these are all late stage, you know, features. These are lineaments. We don't know if they are faults. Some of them have been mapped as faults, not all of them, but we know very, very little about these. So what I wanted to do in this talk, you know, is to sort of walk you through these three areas because it's pretty complicated, and sort of tell you a little bit about how these lineaments relate to seismicity. I plotted these lineaments in ArcGIS. It's sort of a longer-term project to make the lineaments available to the larger community, so people can just basically click on them and sort of understand where they are, who's published on them, what their lengths are, what their names are, and their kind of current status. So this is really the takeaway from this particular slide. What I've done is sort of popped up the different major structures. Here's going to be our the Gorkha event. There were other ones. Here's going to be the Aftershock. I include this 1988 event because this event actually transformed Nepal in terms of their geophysics community. They decided they were going to really start working and sort of organizing themselves as a country to really understand their tectonics, and it was a really significant sort of political event, this magnitude 6.9. The last major one that occurred in the Himalaya, this magnitude 8, occurred in 1934. But what you're going to notice is that where the lineaments cross each other or major faults are going to be very, very close to these earthquake epicenters. I've only plotted up the earthquake epicenters from magnitude 5 to higher. Okay, and it's very clear that every time these lineaments cross, it's like X marks the spot, you're going to get a moderate earthquake, magnitude 5, or sometimes some of these larger ones. Earthquakes are also located along or near some lineaments. I include this sort of Birganj to Kathmandu because they're proposing rail, a high-speed rail that's going to go from these two cities. And some of them are going to be very close to that lineament. Now, you might be wondering kind of like, well, what's the dynamics of those lineaments? This is before the earthquake. This is after the earthquake. You can see that some of those lineaments are probably experiencing some strike-slip motion. That's probably where these strike-slip sort of beach balls come into play. There's more and more strike-slip motion. So I think there's a real possibility some of those are going to be strike-slip. We're going to go over towards the west where we see quite a large number of these sort of cross lineaments. And what's interesting about these is that they kind of creep from these these faults that are under the Indian Craton that are no doubt associated with sort of older structures. They creep, creep, creep. They get into tear fault territory around the main frontal thrust, main boundary thrust, and then they enter the Himalayas sort of as these interesting lineaments. No doubt, lots of crosses. It's where you get some of the major seismic events. The last two that occurred that were pretty devastating to Nepal were these 2022, 2023 events that are sort of the more recent earthquakes that were mentioned in that disaster handbook. Not so large, but it was a problem from sort of a landsliding perspective and the damage over there. Okay, so I haven't plotted up all of them. There's going to be a heck of a lot more of these things coming into play. Okay, the Indians and the Nepalis, they are making roads. This is an example of one of their head race tunnels here that they're building through the Lesser Himalaya Formation. And you can see it's crossing shear zone, shear zone, shear zone, shear zone. These things are all over the place. It says here, it's generally said that in tunnels through the Himalayan rocks, if no fault or shear is seen for 100 meters, that means that it's been missed. Okay, our general framework for the Himalayas is that we have, a few major faults that are controlling the deformation. Well, it's chaos over here. There's several of these shear zones that are going to be coming into play. They're doing this because their rocks are falling down. They need to build the tunnels because this is like a typical road, right, that's running through. This is the Lesser Himalaya Formation. There was no earthquake. This is me trying to get to the main central thrust, and you have this major landslide on a beautiful day, and it's like kind of a pain because within 5 minutes you have a whole traffic jam. And so you've got to build these roads, you've got to consider building these tunnels through these highly sheared rocks because this is not sustainable for some of these countries. So they're also building lots of hydropower tunnels. And so there's going to be a lot more information coming out for the structural community from just the engineering perspective as they start to make these tunnels through Himalayan rocks. And no doubt there's going to be quite a few additional structures that are going to come into play. And this is just another example. You can see fault 5, fault 4, fault 2, fault 1. And they have a lot of trouble building these things. That's what that blast is. It's like extremely intense rock bursts. Okay, these are extremely dangerous engineering structures, but a lot of this information is going to be coming online and really causing a big time rethink of how we think of the architecture of the Himalayas. So I'm going to take you over for just sort of the metamorphic part of this talk is to take you over to the Sikkim, which is where I've been working on some of the metamorphic rocks. And this is the first proposed microplate in the Himalayas. Okay? And so here you have your major thrust fault system, you have the lineaments, and no doubt quite a large of earthquakes associated with strike-slip motion. So the Himalayas actually is going to get broken up in the future, I think, into a zone where you have individual microplates kind of moving around. And so what we do, we go there, we collect the rocks, I date monazite within these rocks, and I've been dating monazite inclusions and garnets, and these are telling us, at what temperature those rocks are crystallizing monazite, and you can see they're like 12 million years old. You can get pressure temperature data out of some of these assemblages, and we have now the ability to really get high resolution records out of maps that look like this. So this is an example also from the Sikkim. What I do normally is to go out there, element map these rocks, and from them I can get very high resolution, detailed pressure temperature paths from these rocks. Okay, I use this theriac domino technique, a data set, sort of bulk rock composition, and an automated routine if you're interested. But basically what I do as a metamorphic petrologist is that I take the bulk composition of the rock, I put it into this program, and it cracks up PT space and tells me what mineral assemblages I can expect at different pressure temperature conditions. And you can see this is telling me that the garnet enters kind of along this isobrad. Biotite should appear here. These are different stability fields. On top of this, I can add the garnet composition and manganese and magnesium, calcium, and all of them converge along a single point. This is the composition of the garnet core. And so I can get a pressure temperature from the garnet core. I can keep going with this same sort of iterative process, and I get very detailed high resolution pressure temperature paths from how these garnets sort of move through the crust. And I take a look at this data and I try to figure out, well, how did this come to be? And what I'm going to tell you is that this pressure, so the rocks decreased in pressure and then increased and were buried. Like, what's causing this? And this is 6 pressure, temperature, time paths from those garnets. They all agree with each other. You know, they also all agree with the garnet zoning, because the process can also make predictions with the garnet zoning. And so in red is the predicted, and as black is kind of like the model. I look at those PT paths and I'm like, how did this work? And I think that those PT paths are not recording necessarily tectonics, but they're recording erosion. And so during that single Gorka event, we had incredible erosion in the Himalayas, and I think that the garnets are actually recording this. So this is what I do. I analyze the garnet composition from core to rim. The garnet is going to grow, be buried. It's going to come back to the surface and then get buried again. That decrease there does not necessarily need to be tectonics. It actually could be surface related. And you may disagree with me, but this is what happened with a single Gorka event. You had extreme erosion, and you have this, multiply this over long, long time scales, you should be able to record it within your higher temperature minerals. So, So this is pretty much, I've been doing this throughout the Himalayas, not just in the Sikkim, also in central Nepal, also in northwest India. We track out these high resolution PT paths, and I put them into models for how I think the Himalayas kind of came to be. And so this is one of the models that we have that shows sort of the main central thrust as a zone of imbrication. And so this is a very simple sort of isotherms that are disrupted by a thrust fault. The rocks go down and up within the shear zone itself. The PT paths are generated. The model actually predicts the PT paths. I compare the model results to what I get from the rocks themselves. The match is great. So in these diagrams, blue is the model, and the colors are going to be my PT paths. Works very, very well. But for me to explain how this rock, these very deep rocks, get to the surface, it requires exhumation of kind of rates of over 12 millimeters per year, which is huge amounts of exhumation. And so, yeah, I want to leave this here with you and potentially have a discussion. I know that there's a lot of people in this room who work on Himalayan tectonics, but this is what I want to get out from it, that you have these lineaments. They extend from the Indian Craton into the Himalayas, and they cut our major fault systems. Okay? And in some cases, those major faults cut them, but we really need to understand them some more. Some of these lineaments are being used to delineate microplate boundaries within the Himalayas, including the Sikkim. And we really have to rethink what we call our Holy Grail. We have lineaments, tear faults, origin parallel strike slip faults that are really causing sort of a modification of the Himalayas as a simple fold and thrust belts. And I do think that there's potential for our higher pressure temperature assemblages to record erosion in the Himalayas. If the Gorka event just caused that one single event, that one incredible, those sort of like landslides, I do think that there's some role for metamorphic petrologists to play in that realm. So thank you so much. I'm going to leave it here.